Welcome back to another Forge College Explainer. So in our last lesson, we looked at the conceptual divide between the Ethereum virtual machine and the Solana virtual machine. We saw how gas on Ethereum basically bundles everything into a single concentric accounting unit, while compute units on Solana decouple things into really granular per-instruction resource metering. But, knowing the theory is really only half the battle. Today, we're doing a complete blueprint teardown of transaction efficiency and cost implications. We're going to look at what actually happens when the rubber meets the road, and how you can truly measure and compare cost implications across these two completely different environments.
50,000. Now, if I tell you a transaction consumes 50,000 gas on the EVM, and an identical transaction uses 50,000 compute units on the SVM, you might logically assume they cost about the same, right? Well, that is a massive trap. Comparing 50,000 gas to 50,000 compute units is literally like comparing 50,000 miles to 50,000 bananas. There is no way to equate them. They measure completely different realities and use entirely different mapping rules to arrive at a final fee. So to really understand efficiency, we need much better metrics.
Okay, let's dive into this. Here is our engineering agenda for today. First, we'll establish the measurement tools. Second, we'll run some transaction stress tests. Third, we'll build the normalization formula. And finally, we'll wrap up with our key takeaways.
Let's jump right into Section 1, the measurement tools.
Think of these 4 items as your absolute baseline efficiency primitives, and each one answers a very specific, highly practical question. Throughput, or TPS, basically asks how many operations can the network process at once. Latency is asking how quickly will an operation become irreversible and visible to everyone else. Per-transaction resource consumption answers how expensive is a single operation in raw platform-specific units. And then finally, we have the effective cost per op, which is kind of what ties this whole shebang together.
So the absolutely crucial point here is that this specific metric, the effective cost per op, is your bridge. It's the thing that translates abstract technical resources, like opcodes and account lookups, into the actual real-world balance draining from your wallet. Right? Because it's not just about how much gas or how many compute units you used. It's about normalizing that monetary cost against a unit of useful work. At the end of the day, what did it actually cost you in dollars and cents to successfully transfer one token or to write one piece of state?
All right, moving on to Section 2, transaction stress tests. So, we're going to apply our tools to 3 common blueprints to spot the hot spots. Our first test is a standard token transfer. On the EVM side, a standard ERC20 transfer uses just a few basic opcodes. But the moment you transition a recipient's balance from 0, boom, you hit a storage write. And in the EVM, storage writes are massive cost outliers. Now look over at the SVM side. The raw compute unit count is completely different. Over there, it's dominated by program invocation overhead and memory operations. So, optimizing your storage layout on Ethereum might literally save your life savings. But spending weeks optimizing that exact same storage on Solana, well, that just makes your code look neat because your real bottleneck over there is the cross-program invocation.
Let's look at test number 2, batched swaps. This is where you interact with the liquidity pools multiple times in a single transaction. On gas-based platforms, repeated opcodes and storage writes just accumulate gas linearly. But batching is highly efficient because you amortize the fixed overhead, like your transaction signing. But on the SVM, well, batching is fantastic, right up until you hit the compute unit limits per transaction. Then you hit a strict breakpoint. Cross that line and your transaction outright fails. You literally have to split it up. So your throughput optimization curve is going to look entirely different depending on the chain.
And our final test is a state-heavy call, something like a multi-step NFT mint. On the EVM, those storage writes carry explicit, heavily weighted immediate costs, plus the implicit long-term state costs. But check out the SVM side. Repeated account access and account size reallocation are what actually drive the consumption here. I mean, this is fascinating, right? The exact same logical operation has a completely different hotspot depending entirely on the platform's metering model. Which brings us to the climax of our teardown. Section 3, the normalization formula.
To really make cross-platform comparisons fair, you have to think about it like this. The EVM is like a combo meal at a fast food joint. Everything is bundled into one price. The SVM, on the other hand, is much more like an a la carte receipt. To compare them fairly, we use this physics-style formula. It brilliantly illustrates that we have to take a vector of our consumed resources, multiply it by the platform's specific weight vector, like gas prices or fee schedules, and then divide all of that by the unit of useful work. This is how we ensure we are actually comparing apples to apples. Let's walk through this mapping matrix. And don't worry, we've spell checked these blueprints twice to guarantee precision. When we look at intrinsic overhead, the EVM maps that to base gas, while the SVM maps it to base compute and rent checks. For pure computation, EVM uses opcode weights, but SVM relies on instruction counts. For storage writes, EVM hits you with a high immediate gas cost, whereas the SVM charges you for account allocation. And finally, for cross-program calls, the EVM charges gas for call opcodes, while the SVM uses compute units for CPI and account lookups. The takeaway here? You absolutely have to break your transaction down into these specific components first.
Now, once you've decomposed the transaction, you have to choose your normalization approach. Are you trying to compare raw technical efficiency, or are you looking at actual wallet impact? You can normalize to a fixed reference price, you could use resource efficiency ratios, or you can go with pure utility, like the actual cost per successful transfer. Just remember that market layer behaviors dictate which approach you should select. A gas fee auction during peak network congestion is going to behave very, very differently than a compute unit environment under that exact same load.
All right, let's wrap this up with Section 4, Key Takeaways.
Let's move to and see how this all builds into a solid engineering framework. Here is your optimization strategy in 3 essential rules. Step 1. Always decompose your transaction into its component parts. Never just look at the raw total. Step 2. Normalize those measurements to a common monetary or utility basis before you even try to compare them. And Step 3. Always measure the batching breakpoints. If you stick to these rules, you won't be misled by raw numbers.
So, I want to leave you with this. Look at your current dashboards and really ask yourself, are your metrics telling the real story, or are you being tricked by the raw numbers? It's a lot to think about for sure. To dive deeper into this subject and master other Web3 concepts, definitely go check out Forge College. In our next explainer, we're going to take this exact mathematical framework and apply it to measuring real transaction costs live on the networks. Thanks for learning with Forge College today, and we'll see you next time.